Hello. Uh, Hello. So, welcome everyone uh, to this week 5 of NPTEL live session on the course of Foundations of Cryptography. First of all, I would apologize that last week I could not take the session at its scheduled time due to some unavoidable circumstances. Uh, However, I will take that session on coming 10th March, which is Friday, on the at the same time, that is 6 p.m. to 8 p.m. and the meeting link will be the same Zoom link as it is now. And as I remember that the last week topic that I was supposed to cover was including the block cipher and practical instantiation of block cipher more specifically, and also the MAC part, some uh, concept of MAC, that is message authentication code. I am assuming that you already have watched those lectures and probably have watched some of the other live sessions that are taken by other TAs. Uh, I will take my session on 10th March on that topic. But I would like to proceed for current week's topics, that is week 5 topic, which includes information theoretic secure MAC and then cryptographic hash function. So for today, I will continue with current week 5's topic, and I would cover the previous topics on next Saturday, that is 10th March. Sorry, next Friday, that is 10th March. And 11th March session will be as usual, it is. Okay. So, okay, that was the first thing to say. And also, because I did not cover the previous week's topics from my side, so I won't discuss the this week, last week's corresponding questions that was posted on NPTEL website. I would take them on next week only. Okay. So let me proceed now, and I will share my screen. Okay. For today's questions. Is my screen visible? Okay, thank you. So this week's broad topics are information theoretic secure MAC or message authentication code, then cryptographic hash function, and then message authentication using hash function. So let us first proceed with the first problem. Select the correct statements from the following. 4 options are given. Perfect secrecy implies zero winning probability of an adversary. Information theoretic security implies zero winning probability of an adversary. Perfect secrecy is achieved in presence of computationally unbounded adversary. Information theoretic security is achieved in presence of computationally unbounded adversary. So you would like to answer? This is very basic concept regarding perfect secrecy that we have already covered in our initial weeks. And then there is also concept of information theoretic security. So would you like to answer the question? I guess this is very basic questions, like conceptual questions. Okay, let me recap once that if you remember, perfect secrecy is about completely hiding any information about the message that is being communicated against adversary which may have unbounded computational power, right? So after that, we moved on to computational secrecy world, where we allow computationally bounded adversary only, or we say polynomial time adversary. And we also allow that the adversary may be able to gain some information about the underlying message that is being communicated by seeing the cipher text. with some negligible probability that we allowed in computational secrecy model. But in perfect secrecy model, even if the adversary is unbounded, we know that adversary has zero probability of gaining any information about the underlying plain text for any ciphertext. Okay. But when we move on to information theoretic security, the main difference is that we allow the adversary to be computationally unbounded. So the adversary can take whatever time it wants to take. Okay. So computationally it is unbounded, but still we unlike perfect secrecy, we actually allow the adversary to have negligible probability to win against the crypto system or to attack the crypto system successfully. So we allow that negligible probability part. So if we compare the perfect secrecy, computational secrecy, and information theoretic security model that we have seen so far, so in perfect secrecy, adversary has unbounded computational power, but still adversary is not gaining any information, or the probability of winning against the crypto system for the adversary is exactly zero. But if we look at information theoretic secure model, then basically it is lying between perfect secrecy and computational secrecy in a sense, because here the adversary is allowed to have unbounded computational power, but then we allow the adversary to still have the negligible probability to attack the crypto system successfully. And then in the computational secrecy model, the adversary is bounded computationally, or it is allowed to perform any kind of computation to gauge the secret or whatever to attack the crypto system polynomial time. Okay, polynomial in the security parameter. And then we also say that adversaries still have a negligible probability to attack the crypto system. Okay, I hope I am clear. And now maybe it is very obvious from the given options that which are the correct statements. So perfect secrecy implies zero winning probability of an adversary. That is true. Information theoretic security implies zero winning probability of an adversary. This is incorrect. Okay, this allows negligible probability of an adversary. Perfect secrecy is achieved in presence of computationally unbounded adversary. Again, this is true. And information theoretic security is achieved in presence of computationally unbounded adversary. This is also true. Okay. So only so first, third, and fourth options are correct. Second option is the only incorrect one. So let me proceed to the next question. Again, this is an basic question about ideal cipher model. So select the correct statements. In ideal cipher model, the adversary is assumed to be unaware of the internal computation of block cipher. In ideal cipher model, the adversary can use block cipher as oracle service and query the oracle in two ways. Davis-Meyer construction of fixed length compression function is collision resistant in ideal cipher model, and then none of them. So I would like to answer. Okay. So in ideal cipher model, if you remember from the lecture, that it was introduced when we were discussing about the construction of fixed length compression function. Okay, so like Davis-Meyer construction is a construction that is used to build a fixed length compression function which are going to be collision resistant, and it was said that the Davis-Meyer construction is collision resistant only if we assume ideal cipher model. Okay, So model is very important in a cryptographical setting because this only determine that how will be the behavior of an adversary or how it will interact with the system. So if you remember the block cipher, so you can think of it as pseudo-random permutation, right? So this is not exactly random. The output is basically pseudo-random of any block cipher, right? Now, also block cipher algorithm itself, like in any encryption algorithm, usually the algorithm is public and known to anyone. But if we assume or we use a block cipher as a black box, okay, so what happens is that we assume that the block cipher service is available to an adversary only as oracle service. So it can query also then actually when we use block cipher, the key k is a secret and unknown to adversary, and upon assuming that the key k is a secret, we say that even after doing polynomial number of queries to the block cipher, your output of the block cipher on an unknown or unseen input is pseudo random. But then here the secret, uh, the key k is not really a secret, rather the query done by the adversary to the block cipher oracle that includes both the key k and the input x. So an adversary can query to the oracle with key k and input x and get back the value fkx when f is the block cipher, right? So in that scenario, and also we say that the adversary is allowed to do two types of queries to the oracle. One is the standard query, that is of the form uh, the adversary provides the input in form of k comma x and gets back y, such that y is fkx. Otherwise, the adversary can query the oracle with key k and some value y, okay, and get back fk inverse y, and it gets whatever it gets, so it knows this is the input x, so it knows that uh, the value of fkx is y. So both the forward and inverse query is allowed. So this is the ideal cipher model to recapitulate. So in now if we see the correct statements, in ideal cipher model, the adversary is assumed to be unaware of the internal computation of the block cipher. So exact description of how fkx is computed using k and x, that is assumed to be unknown to the adversary. So this statement is true. And then uh, in ideal cipher model, the adversary can use block cipher as oracle service and query the oracle in two ways, which is again true. Uh, and then Davis-Weyr construction of fixed length compression function is collision resistant in ideal cipher model. How ideal cipher model helps in arguing the collision resistance of Davis-Weyr construction, that is discussed in detail in the lectures posted. So this statement is of course true. So okay, I'll proceed to the next question. So all of them are correct. Select the correct statements. So SUF, SUF is a strongly universal function. SUF is a special case of L-wise independent function. The next option is SUF is a pairwise independent function. Then knowing the output of SUF for one input, it is hard to guess the output on a new input. And fourth option is none of them. So any answer? So you would like to answer this question? about SUF, strongly universal function. Okay, so if you remember from when we were talking about information theoretic secure MAC, so usually what happens is that like in other cryptographic constructions also, when discussing message authentication code, we initially assumed that the adversary is computationally bounded or polynomial time adversary. Then the adversary is allowed to see polynomial number of message tag pair, or it can query the tag generate tag generating challenger or whatever we say. So the adversary is allowed to make adaptive message query to the challenger, and in response it can see the output tag on that message, right? Now, sorry, 1 minute. Now, in case of information theoretics secure MAC, what happens is that we allow computationally unbounded adversary, but then we allow some negligible probability of the adversary to win. And SUF is some kind of function which we call pairwise independent function, which means that if you see one if you see output corresponding to one input, and then for some new input you cannot properly gauge the output on the new input. So it is just allowing that only one query is allowed on the input. Okay, so in terms of MAC also, the adversary is allowed to only see tag corresponding to one previous message, and then it has to guess some valid message tag pair. Unlike the normal MAC, where the adversary is allowed to do polynomial number of message query to see the corresponding tags, and then it has to guess some valid message tag pair. So now SUF is the concept of SUF helps in constructing one-time secure MAC, which is also information theoretic secure, because even if with unbounded computational power, the adversary is never able to gauge the output on the output tag on some new message, except the random guess from the output space or from the tag space, which is negligible. So the adversary is allowed only negligible probability to successfully generate valid message tag pair only when it has seen one valid message tag pair previously. Now, so if we look at these statements, so SUF is a special case of L-wise independent function. Yes, this is true, because L-wise independent function is analogously mean that the adversary is basically forgetting about adversary. So in general, if you pick any L number of inputs, say x1, x2 to xl, and the corresponding yi, the functional output y1, y2 to yl, are all uniformly distributed over the output space and independent of each other. That is L-wise independent function. So of course, SUF is a special case of L-wise independent function where the value of L is 2. So we also call SUF is a pairwise independent function. And knowing the output of SUF for one input, it is hard to guess the output on a new input. This is also true. So all the statements given are true. Proceed to the next problem. Select the correct statements. So this is actually very basic question about group theory and finite fields, etc. So let me just read out the options once. First option is a group with certain binary operation satisfies closure property along with associativity, presence of identity element, and existence of inverse for each element in the group. Then an abelian group is a group with commutativity. And third option is a field with two binary operations, say addition and multiplication, is an abelian group under addition. Also an abelian group under multiplication when considered excluding the additive identity, and its multiplication distributes over addition. So, anyone would like to answer? So, okay. So, recalling the definition of group for once, that what is a group? Group is a set of elements with some certain binary operation defined on it, and it satisfies closure property. Closure property means that uh, pick any two element from the set given, and you perform the particular binary operation which is associated with that set. Performing binary operation between those two element of the set returns an element which is again belongs to that set. So that is the closure property. You perform the binary operation among any pair of elements from that set, and you get back elements from the same set only. So then we call that the set satisfies closure property with respect to that binary operation. Binary operation means that particular operator takes two input. So that's why it is binary operator. Like in normal arithmetic, addition can be treated as binary operator. In Boolean arithmetic, you can treat and or XOR. All of them are binary operator because it takes two inputs at a time and adds or multiplies or performs ANDing, XORing, etc. So that is binary operator. So a set with that kind of binary operator satisfying closure property will be called group only if it also satisfies associativity, presence of identity element, and existence of inverse of each element in the group. So associativity means, say A, B, C are three elements of the group, and so A plus B, you perform A plus B first, and then on the output you perform plus C again. So A plus B inside bracket plus C is equal to the A plus inside bracket B plus C. So in whatever order you perform the addition, you get the same result back. So that is the associativity property. And presence of identity element is one particular element in that set, such that you take any element A of the group, or I should say of the set, you take any element A from the set and you perform let's say the operator is plus, so you perform A plus that particular element, let's call it I, the identity element. So A plus I will always give you back A, and that is the property of identity element. So there should be one such a particular element I, such that any element of the set with the binary operator applied on I give you the same element A back. So that is the property of identity element. And existence of inverse for each element in the group means that there should be some let's say A is some element of the group, so there has to be another element B in the group such that A plus B returns the identity element I. I am telling plus because now I am considering plus to be that particular binary operator. It can be any other binary operator corresponding to whatever group we are talking about. So basically, for each element A in the group, there has to be some B in the group such that A plus B returns the identity element I. Then only we say the set that satisfies these three property: associativity, presence of identity element, and existence of inverse for each element in the group in the set. So that set is only called to be a group. So as you see that the first statement is obviously correct according to the definition of group. And the second option given is that an abelian group is a group with commutativity. This is a true statement. And just to recap, what is commutativity? That is, you take any two element A and B of the group, and let's say plus is the binary operator that we are talking about. Then A plus B, if is always equal to B plus A for any two element A and B of the set, then we say that the group is an abelian group. Okay, so this is true that abelian group is a group with commutativity. All the properties of group have to be satisfied, and with that, commutativity is the another extra property that has to be satisfied to make the group abelian. The third option given is that a field with two binary operations, say addition and multiplication, is an abelian group under addition. Also an abelian group under multiplication when considered excluding the additive identity and its multiplication distributes over addition. This is true because that is what is the definition of field. So field is also another algebraic structure, but with augmented with two different binary operator. When we are talking about group, we are talking about one single binary operator defined on that group having closure property. Now, when we talk about field, we say that there are two different binary operator. Usually, we refer them as one as addition and another as multiplication. And addition operator is such that with the addition operator, the all the elements of field actually satisfy the abelian group property. Okay, and if we just discuss the additive identity element of from that set, if we discard that element, so except that one element, the rest of the set of elements satisfies the abelian group property under multiplicative operator. Okay, and not only that, its multiplication distributes over addition. What we mean by that is, let's say dot is the multiplicative operator and plus is the additive operator, addition operator. Then we say that A dot B plus C is equal to A dot B plus A dot C. That is what we mean by multiplication is distributed over addition. Okay. So all these properties are of course satisfied by a set of elements, and then only we call that set of elements as field. So this option is also correct. So basic purpose of discussing this question was that we should once recap the concept of this algebraic structure. So as you have already understood that all the three options are correct. Okay. So let me proceed to the next problem. So just now we discussed the concept of group and abelian group, and this is a question on that. So if you would like to answer, I will pause for some time, and if you would like to answer, it is here. Of course, plus is the addition binary operator. This into symbol is multiplicative binary operator. R is the set of real numbers and Z is the set of integers. So you would like to answer? Okay. So real number with multiplication is not a group. Okay, if this meeting ends, then you can join in the same link again. Okay, this will end in 10 minutes. Real number with multiplication is not a group because the element 0 is also included in the set of real numbers, and you see 0 is not invertible. So usually the multiplicative identity, if it is there in the set of real numbers, it is 1, because let's say 2 is a real number, and then 1 by 2 is another real number, and you multiply 2 and 1 by 2 and you get back 1, which should be the multiplicative identity element. But then 0 is such an element of which no inverse exists, because 1 by 0 is undefined. So if we consider excluding the element 0, then yes, R excluding 0 is a group under multiplication, but not the whole group R. R minus 0 with addition operation, is it a group? It's not, because without the element 0, there is no additive identity element in the set R. Okay, so 0 is the obvious identity element for the set of real numbers, as well for the set of integers. So if we consider the set Z, for that also 0 is the additive identity element. So if we exclude the element 0 from Z, then it is no more a group under addition. So among the options provided here, of course, the first 3 options are incorrect, and the only correct option is the fourth one. Okay, next question. So here you have been provided with some construction with a function h, and you have to check whether, rather you have to prove that the provided option h is a strongly universal function. So L is some constant greater than 0, and you have a prime P. Key space K is defined as Zp to the power L minus 1, which means that L plus 1 sized vector where each element is coming from Zp. By Zp, you mean the set 0 to P minus 1 modulo P, right? So congruence modulo P, all the elements of 0 to P minus 1. The message space is Zp to the power L size vector with each element from Zp. Tag space T is Zp itself. H is defined over K cross M to T, such that you have this L plus 1 sized key with each element denoted as K0, K1 to KL, and the L length message is also denoted as M1 to ML with individual element denoted as MI. Now the function outputs K0 plus summation of Ki Mi mod P. You have to check if it is strongly universal or not. If you remember, just a few times ago we discussed that the property for a function being SUF is that that function is pairwise independent. That is, you have two inputs x1 and x2, and the corresponding output y1 and y2 has to be distributed uniformly over the output space, which is the tag space here, and they will be independent of each other. In other words, we can say that h of x1 is equal to y1 and h of x2 is equal to y2. That probability is nothing but exactly 1 by t square, or I should say the size of t, square of size of t. The tag space is t, so size of the tag space, if we denote it inside the mod symbol, mod t, so 1 by mod t square should be the exact probability of happening that h of x1 is y1 and h of x2 is y2. Okay. So to show that h is strongly universal, how we proceed? So as I just mentioned that here h of x1, that is let's say m is one message and m dash is the another message, and the corresponding output or tag, let's assume it to be t and t dash respectively. So we need to calculate the probability that h of m with this key k will output t, and h of m dash with respect to the same key k will output t dash. What is the probability of occurring these two together? Okay. So if we analyze the left hand side part, what happens is that we replace this functional value h with k0 plus summation of ki mi equal to t, and this is k0 plus summation of ki mi dash equal to t dash. So what we get is that if both these equation has to be satisfied, we can write by subtracting this from this. So you subtract the second equation from the first equation so that k0 gets cancelled, and we are left with summation of ki mi minus mi dash equal to t minus t dash. You subtract this from this. Okay. And also remember, each of the element ki, mi, all of them are element of zp. Also t and t dash, they are also element of zp. Okay. So we need to calculate the probability that summation of ki mi minus m dash I is equal to t minus t dash. So to analyze this, let's assume that I star is the largest index such that m I star is not equal to m dash I star. Okay. Then you can write this as, so I star is the largest index, right? So you have a few elements before I star, that is I equal to 1 to I star minus 1, elements which are to the left of the element I star by position. For that you write ki into mi minus mi dash for these number of elements, and then the particular element ki star into mi star minus m dash I star plus the elements right side to the I star by position. So that is I equal to I star plus 1 to L. Total L number of elements are there of the form mi or m dash I. So this is how we break the summation expression ki mi minus m dash I. We break them in three parts, keeping the I star one particular index calculation in between. Now notice that the right side part becomes 0 for any arbitrary value of ki. Why? Because I star is the largest index, so that mi star is not equal to mi dash star. That means after I star, for any index position, mi is equal to m dash I. So this becomes 0, mi minus m dash I. So for any arbitrary value of ki, this part will always be 0. Okay. So the left part is that I equal to 1 to I star minus 1, ki mi minus m dash I, and ki star into mi star minus m dash I star. This should be equal to t minus t dash. Now also notice that in this equation, all the mi and mi dash values are known, right? You know the value of mi and the value of m and m dash, and so each index, the value of each index position of m or m dash, right? And you also know the value of t and t dash. Now what you do is that you populate ki's for all the rest of the positions. So leaving the particular position I star, you fill all the L minus 1 So basically, you fill all the positions of K, leaving the position I star only. So all the L minus 1 number of uh, positions in L are filled up with arbitrary values from ZP. Then you have all these values calculated of the form Ki and M dash Ki into Mi minus M dash I, because M and M dash values were already known and you are assigning arbitrary value from ZP to all these Ki's. Okay. Now see that having known this summation value in the left hand side and having known the value T minus T dash, also having known the value Mi star minus M dash I star, you can uniquely compute Ki star. Is that true? So you know this value, you can just subtract this part here. So you get Ki star into Mi star minus M dash I star equal to T minus T dash minus summation of I equal to 1 to I star minus 1 Ki into Mi minus M dash I. All these right hand side value will be known to you. And also notice that Mi star minus M dash I star being an element of Zp, where P is prime, must be invertible. So remember, for any prime P, the set Zp, except the, or I should say the set Zp star, which means that you just exclude the element 0 from the set Zp because 0 is not invertible anyway. So all the elements, if we recapitulate just a little bit, for any integer n, the elements in the set Zn which are co-prime to the value n are part of the set Zn star. Okay. And those elements are invertible as well. Okay. Now, as P is prime, all the values lesser than P are of course co-prime to P, right? But we have to leave 0 because 0 is not invertible. So we are left with the elements 1 to P minus 1. So all these P minus 1 elements of the set Zp star are invertible. And Mi star minus M dash I star, this value is not 0 because we have already assumed that I star is such an index such that Mi star is not equal to M dash I star. So this difference is never 0. So this difference being belonging to Zp star is invertible. So we can compute Ki star equal to T minus T dash minus summation of I equal to 1 to I star minus 1 Ki into Mi minus M dash I into inverse of Mi star minus M dash I star. Okay. So like that way, we can get unique value of Ki star. So remember, except the position I star, for all the L minus 1 elements of K, we assigned random values. So for each set, so for L minus 1 position, how many number of possible set of values can be assigned, with each element being belonging to Zp? So that number of possible cases of assigning different values from Zp to the L minus 1 index positions of K is P to the power L minus 1. Simple. So, and for each of those P to the power L minus 1 possible set of values to K, we will have one unique solution to the value of Ki star. And once you get the value of Ki star, just notice that you can replace the value of Ki star to this equation, to any of this equation, that is h of m equal to t or h of m dash equal to t, to any of this equation, you can replace the value of ki star, and you have already kept the other values, other index position values of k ready, which are assigned arbitrarily from zp. And with that, k0 can be calculated uniquely. Okay, so basically you now have all the values of all the solution of values for k0 and ki star with all the other L minus positions values assigned randomly, and that possibility is p to the power L minus 1. And in general, the size of the key space is p to the power L plus 1, because if you remember, the key space is zp to the power L plus 1. So in general, number of keys possible are p to the power L plus 1. Now, if by seeing these two equations, that h of m equal to t and h of m dash equal to t dash, we can how much is the probability that we guess these two values correctly? That is nothing but p to the power L minus 1 by p to the power L plus 1 by simple probability. And this gets us back 1 by p square, which is again, p is the size of the tag space zp. So we can write it as 1 by mod t square, or mod t square. Okay. So, and also that is the probability of strongly universal function. That the probability of any, if f is a SU f is a strongly universal function, then f of x equal to y and f of x dash equal to y dash, both of them will be satisfied with probability 1 by size of y, size of the range set squared. That is p here, the size of the tag space. So thus we can conclude that h is indeed a strongly universal function. Next, I proceed to the next problem. This is also regarding proving strongly universal, proving a function strongly universal. Let's look at what is the function given here. So L and N are some constant greater than 0. Let K, the key space K, to be 0, 1 to the power L cross N into 0, 1 to the power L, which means that there are, the key consists of one matrix and one vector. The matrix has size L cross N and the vector has size L. And of course, both the matrix and vector are Boolean matrix and Boolean vector. And you have been given a message space which is n-sized Boolean vector, and the tag space is L-sized Boolean vector. You define the function h as k cross m to t as h of kv with input m returns k dot m XOR v, and all the operations are performed modulo 2. Of course, XOR is nothing but addition modulo 2, and the multiplication is also said to be performed in modulo 2. Now prove that h is strongly universal. I will pause for a minute. So we are discussing about h being strongly universal. And H description of H is given as that, where the key is consisting of some matrix K and some vector V, and applied on incised incised vector M, and the output is K dot M XORed with V. You need to show that H is strongly universal, and to show that any function is strongly universal, what we basically need to prove is that H of M equal to T and H of M dash equal to T dash, the probability should be equal to 1 by size of function output space square. Okay, so we will try to do exactly that in this question as well. So I hope the screen is visible. Now, again, just like the previous problem, K dot M plus V equal to T and K dot M dash XORed with V equal to T dash. This we can write as we subtract the second one from the first equation, the second equation from the first equation, to cancel out V from both of them, and we get back K dot M minus M dash equal to T minus T dash. So if we now just analyze the structure a bit closely, the matrix K has the dimension L cross N, okay, and the vector is a n-sized vector. This is a column vector. Now we assume I star is the largest index such that M I star is not equal to M dash I star. So in this vector M minus M dash, I star is the largest index where the value of Mi minus M dash I is 1. Basically, all of the element of both matrix K and vector V and message M are from 0, 1 space. So if Mi star is not equal to M dash I star, then that means Mi star minus M dash I star is 1. And for all the index I greater than I star, Mi minus M dash I will always be 0. Anyway, we will analyze in quite similar fashion as the previous problem here also. So we fill all the values of matrix K with arbitrary 0, 1 values except the I star column here. So let's say we the box I have made here in the matrix, let's say this is a column in the I star position. So we leave this column to be determined later. So we don't fill any values to this column. We fill all the rest of the elements of the matrix K. So what are the number of rest of the elements in this matrix? So you have total L number of rows and you have N number of columns, and you are leaving one column undetermined for now. So the rest of the number of columns is N minus 1. So you have L into N minus 1 number of elements that are that you are filling arbitrarily with the values 0 and 1. Okay, you are done with assigning those arbitrary values to L into N minus 1 number of elements of K. And coming to this right hand side vector, which is T minus T dash, you know the value of T, you know the value of T dash. So you know the each of the elements value in this vector T minus T dash. And you also know all the values of the vector in this vector M minus M dash. Okay. Now, can you determine the I star row, I star column in the matrix K? Yes, you can, because how it is computed? So simple matrix vector multiplication, if you consider, so you take, let's say, the first row, you perform vector dot product with this column vector M minus M dash, right? So as all these elements are 0, so they will be added up to 0 till here, and this is known to be 1. And all the upper elements, that is the elements having row number less than I star here in this vector, are known, and you have filled up some values to the elements which have column number less than I star in the first row. So you know these values, you uh, you multiply them element by element, and you add up all of them. So basically how you do the vector dot product, right? The first row of matrix K and the column vector M minus M dash. You multiply them with only this element unknown, okay? Only this I star element in the first row is unknown. All the rest of the values are known. So this is obvious that you can determine this value such that it maps to the targeted element in the vector T minus T dash. So this is how you can determine the I star element in the first row of matrix K. And in the similar manner, you can determine one after another all the L number of values corresponding to this I star column of the matrix K. Okay, once this is retrieved, this I star column is retrieved, you have the whole K matrix. You have values assigned to this whole K matrix. And with this in hand, you replace this value of matrix K here. Let's say in this equation, K dot M XORed with V gives T. You know the value of T, you know the value of K now. You also know the value of M beforehand. So you can determine the value of V uniquely. Okay. You can replace the matrix value K in either this equation or this equation, anywhere you want, and you get back the unique value of V. Now, you notice that with you've assigned basically L into n minus 1 number of arbitrary values to matrix K, and for each such assignment, you will get unique value to I star column and the vector V. So how many is the possibility of assigning values to L into n minus 1 number of elements in matrix K? That is essentially 2 to the power L into n minus 1, because all the elements are either 0 or 1. Easy calculation now. Now, what is the size of key space of this construction? So as there are one matrix and one vector of size L cross N and L respectively. So the whole key space has the size 2 to the power. This is ln. So 2 to the power ln into 2 to the power L. So that is 2 to the power ln plus L. That is the whole size of key space. And for each such 2 to the power L into n minus 1 number of assignment to the n minus 1 column of K, you have unique values of I star column and V. So the number of possibilities there is 2 to the power ln minus L. L into n minus 1, that can be written as ln minus L. Now you calculate the probability of collision. That is the probability that you guess this value T dash correctly. Okay. So probability of you pick any random M and M dash, and you pick any random T and T dash, and the probability that these two are satisfied is that probability is 2 to the power ln minus L by 2 to the power ln plus L, which gives you 1 by 2 to the power 12, and it can be written as 1 by 2 to the power L square. And 2 to the power L is nothing but the size of key space here. Notice that the size of tag space. Tag space was provided as L-sized vector of L-sized binary vector. So tag space is 2 to the power L essentially. So we see that the probability of collision is 1 by this is not collision. Basically, this is a probability that you pick any random m and m dash, and you pick any t and t dash, and you find that this is indeed correct assignment with respect to the function h defined. Okay, so that probability is 1 by mod tau square, and that is expected from a true AC wave. So indeed, this given function h is a AC wave. It is proved. Okay, I hope I am clear. So I'll proceed to the next question. So a Toebles matrix A is a matrix where Aij is equal to Ai minus 1, J minus 1, where Ij is greater than 1. So this is a kind of type of matrix defined such that Aij equal to Ai minus 1, J minus 1 means that all you consider any diagonal of the matrix and all the diagonal elements will be equal to, will be same basically. Okay, now the values along any diagonal are equal. Now you are given key space K, which is represented as x to the power L cross n cross 0, 1 to the power L, where x denotes the set of all Toebles matrix. Measure space M is equal to n-sized binary vector. Tag space T is L-sized binary vector. You define the function h, k cross m to t, as h of kv of m is k dot m XORed with v, all operations performed in modulo 2. Prove that h is strongly universal. What is the advantage here compared to the construction in the previous problem? Okay, so the construction, as you had seen in the previous problem, is exactly same. That is k cross m XORed with v. K is again a binary matrix and v is a binary vector, but only difference is that in the previous problem k was any random binary matrix, but here K has certain structure. K is a Toebles matrix where all the diagonal values are same. So we analyze the same problem in the in a different scenario. Okay. So just to proceed, let us first examine that what is the size of key space for Toebles matrix. So just to visualize how the Toebles matrix looks like, I have drawn here a 5 cross 7 Toebles matrix. So this element at the top right corner, this is alone. So because it is not part of any other longer diagonal, so this is alone. But then if you consider just the element left to it, it has the same value with the element right to it. So, and similarly here there are say 3 elements with same value aligned with this diagonal, 4 elements here, and like that it continues. Okay, so all these diagonals that are shown in this figure in the matrix, all of them have same value. Okay, and this bottom left corner value and top right corner value, they are alone. I drawn this just to make the structure of Toebles matrix clear to you. Now see that the what is the number of Toebles matrix present for fixed value of L and N. That is, you say that let's say you first populate all the elements in first row. Okay. And this immediately fills up all this value till here, right? The first row, first column element will be same to all the diagonal elements here. The next element will automatically assign all the element here aligned with this diagonal, and like that. So the only remaining values that are remain to be assigned here are this triangular shape region. These values are yet to be assigned. So you have to assign values to the first column element also. So this first row element, that is n number of elements, are already assigned, and then you need to assign the rest of the elements of first column, that is L minus 1 number of elements, and that determines the whole all the other values of the matrix as well. So that gives you a total. You have the liberty to choose n plus L minus 1 number of values, right? So the Toebli's matrix count becomes 2 to the power L minus 1. And the key space is defined as this Toebli's matrix along with another vector of size L. So in total, the key space becomes 2 to the power n plus L minus 1 into 2 to the power L. That gives us 2 to the power n plus 2L minus 1. That is the whole size of key space. Now we analyze that how we calculate the probability of h of m equal to t and h of m dash equal to t dash, just as we mentioned in the previous problem related to SUF. So again, we get the same equation that we need to calculate probability k into m minus m dash equal to t minus t dash. Here, all the values of m, m dash, t and t dash are known to you. So we just apply some trick here of filling up the matrix K. In the previous problem, we just fixed the one, we just left one column, I started column of the matrix, and all the rest of the columns of K were filled up arbitrarily with 0 and 1. Okay. But now, as just because of the structure the Toebli's matrix has, what we do is that we proceed in this way. So again, assume that I star is the largest index with mi star not equal to m dash I star. Now, we first fix, we proceed from bottom to top. Okay, so we first try to fill the last row of the Toebli's matrix. So we first fix I star minus 1 entries of last row. Okay, I star is the column after which corresponding to mi element, mi and m dash I, those are equal to each other. I star is the index where they two differ, and we first fix I star minus 1 number of I star minus 1 number of elements in the last row as marked in the picture here. And then you see that the I started entry of the last row is uniquely computed with that. Why? Because irrespective of whatever value we assign to them, although we are not assigning anything to them, but irrespective of whatever value it would have been assigned, because mi and m dash I has the same value in these positions, this will return you 0. So only values that matters in the computation of dot product with the last row with the vector m minus m dash are these elements, and these values are known. M minus m dash values are known, and with that information you can compute this I started element of the last row. So I started element of the last row can be uniquely computed. So you have this I star number of elements of last row already sorted. Now, due to the structure of Toebli's matrix, just notice that this second element of the last row will exactly be equal to the this element, okay, diagonally positioned element. So the second to last row can be filled up with this I star number of values one after another till this point. So again, I star minus 1 number of elements in the second to last row are filled up from the last row. And then in the similar manner, I star element of the second row can be uniquely computed, irrespective of whatever value you would have been assigned to the writer columns of the second to last row. Okay. Now, when this value is uniquely computed, then again moving up, we can get back I started number of elements computed here. So we proceed this way just to pictorially represent this thing again. So first we have this K matrix where we are arbitrarily assigning this I star minus 1 number of elements in the last row. In the next step, we get the I starred element of the last row uniquely computed. After that, we get, in the third step, we get I star minus 1 number of rows, I star minus 1 number of values in the second to last row assigned by the property of Toebli's matrix. Next, we get this I starred entry of the second to last row computed uniquely as we know rest of the values. Okay. Then in the fifth step, actually, when you determine the I starred entry of the second to last row, this will be exactly equal to the diagonally positioned element in the last row. So this element, just I star plus 1th element of the last row is determined from this value of the second to last row. Okay. Hope I am clear. So that is in the fifth step. Proceeding in the same way, now we again from the I star number of values already computed in the second to last row, we get I star minus 1 diagonally positioned element of the third to last row in the next step, that is the sixth step. And then we get the I starred element uniquely computed in the third to last row. And then in the next step, this element will exactly be equal to the I star plus 1th entry in the second to last row. And in the next step, this element, element denoted as 8, this element is again same as the diagonally positioned element in the last row. So like that, you will get the elements filled up step by step. So, okay. You will get the elements computed step by step like this. And proceeding in the way, we see that only n minus I starred rightmost element of the top row are left to be uniquely determined. If you see the overall structure of the matrix after this computation is done, so I star number of elements till the first row have already been computed. Only this number of trigonal shape of region with elements in the matrix are still need to be filled up in the matrix after this process completes. Okay. So we see that only the rightmost n minus I starred element in the first row, if we fill up, then automatically the diagonal elements will be assigned in the same way. So remember that the assignment of only n minus I star, only I star minus 1th number of elements in the last row were in our hand. After that, all the values that we seen getting filled up in the matrix were not in our control. They were either uniquely getting computed in case of I starred element of each row, or they were automatically getting filled up following the property of Toebli's matrix. So like that, we see that only n minus I starred rightmost element of the top row are left to be assigned. So we have the control to assign only I star minus 1th leftmost element of last row and n minus I star rightmost elements of the top row. Okay. So and that number of possibilities is of course 2 to the power I star minus 1 plus n minus I star, which gives us 2 to the power n minus 1. And remember, the size of T space we had already seen for the function h is 2 to the power n plus 2l minus 1. So we get that as 1 by 2 to the power l, which we can again write as 1 by 2 to the power l l whole square, and 1 by 2 to the power a, and 2 to the power l is the size of tag space. So we see that the property of h is exactly matching with the property of a AC wave, the requirement of being AC wave. So h is a AC wave, we conclude. Hope this example was clear to you. How this was quite a tricky example, but I hope the calculation was understood by you. Okay. So let me proceed to the next example. Next problem. So define an appropriate notion of a 2-time epsilon secure MAC and give a construction that meets your definition. So anyone would like to answer? We have already seen 1-time epsilon secure MAC, right? So 1-time epsilon secure MAC ensures that the adversary, if provided with provided with tag corresponding to one message of its choice, but the adversary is then unable to return a valid message tag pair with some new message, of course. So analogously, if you try to define 2-time epsilon secure MAC, epsilon is nothing but the probability that the adversary wins, or the adversary is able to successfully generate a valid message tag pair. That probability is upper bounded by epsilon. So just like 1-time epsilon secure MAC, if we want to construct a notion of 2-time epsilon secure MAC, what would that be? Anyone would like to answer by unmuting them? Okay, so this is very general or basic notion. So here, instead of allowing one query to the adversary, we will be allowing two queries to the adversary, right? So now the adversary is able to make query on two messages of its choice. Say it can query for M1 and get back to see the corresponding tag T1, and it can query M2 and it can see the corresponding tag T2, and then it has to output one message tag pair M star comma T star, and we say that this 2-time MAC is epsilon secure only if the probability that M star T star is a valid message pair tag is upper bounded by epsilon. Okay, so this is quite obvious notion. And now the next part is that give a construction. Okay, let me just go back to the previous question once. I guess I missed one part to discuss. That is, it was given another part of the question, that what is the advantage here as compared to the construction in the previous problem. In the previous problem, actually, the construction of H was same, K dot M XORed with V, but the matrix K was general binary matrix. But in this problem, we were talking about 12 matrix. The advantage here is that if you see, the key space is quite lesser because of this particular construction of 12 matrix, the number of 12 matrix count is just to the power n plus l minus 1, leading to the key space size of n plus to the power n plus 2l minus 1. Whereas if you see the previous example, there the key space size was all to the power nl plus l, because there are nl number of elements in the matrix. For that comes the part 2 to the power nl, and there are the secret vector v whose size is l. So in total you get the key space size as 2 to the power nl plus l, but here it is just 2 to the power n plus 2l minus 1, which is quite less. So the key space is quite less. Okay. Great. Sorry for just interrupting to the previous question. Now, coming back to this question, yes, the construction is clear, I hope. Now, if so, the notion is clear for 2 time epsilon secure map, and the question is give a construction that meets your definition. So that construction is also can be analogous to the 1 time epsilon secure map construction that we initially studied. So we actually think of some group ZP, talking about 1 time epsilon secure map. We think about some group ZP, and we choose uniformly random elements, say A and B from ZP. And then for any message M, we calculate tag as A dot M plus B, where not group, I should say actually ZP as field for any prime P, finite field. And addition and multiplication are defined in modulo P. And then A dot M plus B is the tag computed on the message M. And this construction was shown to be 1 time epsilon secure, where the value epsilon is 1 by P square. So that thing was discussed in your NPTEL lecture by the professor. So in case of 2 time epsilon secure map, basically you can extend that idea that you again take the field, say ZP, and the key, instead of choosing 2 random elements from the field, you choose 3 random elements from the field and say elements are K1, K2, K3. So there the secret was A and B. Here the secret is K1, K2, K3. And for any message which are element of ZP, you compute the tag as K1 M square plus K2 M plus K3. So this is a degree 2 polynomial. In case of 1 time epsilon secure map, you use degree 1 polynomial of the form A dot M plus B. Here you extend analogously the same idea to the degree 2 polynomial in order to get a 2 time epsilon secure map. And again, the winning probability of the adversary, or the probability of generating a valid tag on some third unknown message gets down to 1 by size of tag space cube. Okay. Okay, proceeding to the next question. Here, so let me read out the question once. Let pi 1, tag gen 1, tag verify 1, and pi 2, tag gen 2, tag verify 2 be 2 max systems over the key space K, which is defined as n size binary vector. And here the key generation algorithm for both pi 1 and pi 2 outputs a random key from the key space. It is given that either pi 1 or pi 2 is a secure MAC, but which one is not known. So which of the following is or are true? We have been given option as pi, let's say, is another MAC system consisting of the 2 algorithm tag gen, tag verify. That is a secure MAC over key space K equal to 2n sized binary vector, where tag gen K1 concatenated with K2 applied on M returns tag gen 1 on M with respect to key K1 and tag gen 2 of on M with respect to key K2. So your tag gen algorithm for the new modified MAC scheme pi basically outputs the tags that would have been generated by the first scheme and the second scheme, and they together are output as tag of the modified scheme. And then tag verify works as follows. Tag verify on M sigma 1 sigma 2, where you can think sigma 1 to be the tag generated using the tag gen algorithm of pi 1, and sigma 2 is the tag using the tag generation algorithm of pi 2. And the tag verify on M sigma 1 sigma 2 with the keys K1 K2 returns 1, or this is considered to be a valid tag if and only if tag verify on message tag pair m sigma 1 with respect to q1 returns 1, and tag verify on message tag pair m sigma 2 with respect to key k2 returns 1. And the second option is similar, only difference is that the tag verification algorithm accepts m sigma 1 sigma 2 as a valid message tag pair if and only if tag verify is satisfied for scheme pi 1 or tag verify is satisfied by scheme pi 2. And then options are none of the above construction is secure and or both the constructions are secure. So you have to comment on the left. Anyone would like to answer this question? Say intuitively or something. So I would rather say just think about the first two cases, that whether the tag verification should be given as 1 in the scheme pi if both the verify scheme accepts m sigma 1, m sigma 2 in their corresponding protocol, or any one of them accepts it, that will do to remain the system pi secure. Okay, I would suggest that a MAC system is considered to be secure only if an adversary is unable to generate valid message tag pair on some unseen message M. Right. So intuitively, if you think of, so it is given that pi 1 or pi 2 is insecure, or any one of them is secure, but you don't know which one. So without loss of generality, let's think that pi 1 is the insecure MAC. So pi 1 is not secure. What it implies is that in polynomial time, an adversary is able to generate some message tag pair, say m comma t, such that the tag verify 1 algorithm accepts mt as valid message tag pair. Okay. Now, an adversary who is trying to break the system MAC system pi, it may try with the same pair m comma t to verify that if it is a valid message tag pair with message tag pair with respect to MAC scheme pi as well. Then what happens is, if tag verify of the modified MAC system pi works in the way that any one of the verification algorithm, verify 1 or verify 2 accepts, then it accepts. What happens is that as pi 1 is insecure and the adversary is actually able to generate the valid message tag pair m comma t for pi 1, so this verification algorithm will satisfy 1, will give 1. So the output of OR will be 1. So basically, m comma t, if it is a valid message tag pair for pi 1, as pi 1 is insecure and it is generated by some polytime adversary, then m comma t will be a valid message tag pair for the scheme pi as well, making pi insecure. But we want pi to be secure MAC. So generating valid message tag pair should be difficult for a polytime adversary. So we should go with the AND option, such that even if tag verify 1 returns 1 due to the case that pi 1 is insecure, still tag verify 2 will return 0, and so the AND condition will overall make the tag verify k1 concatenated with k2, this algorithm, to output 0. So this empty pair will not be accepted by pi, so pi will continue to be remain secure. So we go with the first option. I hope I could make the analysis clear. So let me proceed to the next question. Here again comes some MCQ question. Select the incorrect options for the Merkel-Damgard transformation. First option is given as, it employs a multi-stage approach and used in many popular hash algorithms like MD5, SHA-256. Second option is this construction will always add a padding to the message which depends upon the length of the message. The initial vector IV used in this construction can be randomized. The transformation is a deterministic function of the input. So you would like to answer this question? This is from Merkle-Damgard transformation, which this transformation, if you remember, is used to construct cryptographically secure hash functions from for any arbitrary length message input, assuming the existence of fixed length collision resistant compression function, right? So okay, so for Merkle-Damgard transformation, this is a correct statement that is it is a multi-stage approach where basically if you assume existence of compression function, collision resistant compression function, which let's say takes input of length n plus L and outputs hash value of length n only. So this kind of compression function are used in various stages, and the using some fixed initialization vector IV and using the arbitrary length message M, we divide the message M in different blocks of size L, and then each of the block are fed into this compression function at various stages, and finally we get output, some hash output of out of that. Okay, so yes, it is a multi-stage approach, and it is indeed used in many popular hash algorithms. Then first statement is correct. Then this construction will always add a padding to the message which depends upon the length of the message. Yes, this is true, because for variable length message, if we are dividing the message into several blocks of fixed size, say L, so the message may not be always multiple of L, and it may vary, it may have varying size. And so to remove any kind of ambiguity, and for that we add one last block of message which can have some information in it and then padding, or it may be a completely padding block depending on the scenarios. So this statement is true, that there is this scenario of padding to the message. Okay, the initial vector IV used in this construction can be randomized. This is not a correct statement, because the IV is fixed and known. Whoever is trying to use the hash function. The transformation is a deterministic function of the input. Yes, it is deterministic, because with the fixed message with a fixed message and fixed IV, we always get the same hash for the same message. So this is indeed a deterministic function. So only incorrect statement is the third one. Here comes another multiple choice question. So given H is a collision resistant hash function, then which of the following is or are false? The function h1x expressed as h of x concatenated with h of x is not collision resistant. The second option says that it is collision resistant. The third option talks about another possible construction, h2x equal to 1 concatenated with hx. So the question is whether it is collision resistant or not. So so let me proceed. So both these construction given h1 and h2, we say that both of them are collision resistant. How? That we will see. So for the first case, h1x expressed as hx concatenated with hx, let's assume it is not collision resistant first. Then it will imply that there is a polytime adversary who is able to output two inputs, say x and x dash, such that h1x is equal to h1x dash. That's what we mean by collision pair. So if it is not collision resistant, then any polytime adversary is able to return such pair of inputs that leads to collision, right? Now h1x equal to h1x that implies h of x concatenated with hx uh, equal to hx dash concatenated with hx dash by the definition of h1x, right? Now this clearly implies that each half of the left hand side string matches with corresponding half of the right hand side string. So this is very obvious, right? If this is equal to this string, then hx is obviously equal to h of x dash. Otherwise, it would not have been the same string. So this implies in turn that for the function h also, we find the collision pair x and x dash. So if there is a polytype adversary who is able to output collision corresponding to function h1, we can use that adversary to output collision for the function h as well. But we already know that h is a secure cryptographic hash function. So it is possible for any, it is not possible for a polytime adversary to easily output such x and x dash collision pair except negligible probability. So this is a contradiction, and we conclude that h1x is indeed collision resistant. And similar argument can be followed in case of the second option also. So h2x is again given as one concatenated with hx. If it would not been collision resistant, then it would imply that there are collision pair x and x dash output by some polytime adversary such that h2x is equal to h2x dash, and which implies that one concatenated with hx is equal to one concatenated with hx dash, and just leaving the first one, the rest of the string also should match, and which implies hx is equal to hx dash, and this implies that x and x dash can be used as collision pair for the function h as well. So, but we already know that h is secure hash function, so such x and x dash finding should not is not actually easy for any polytime adversary. So this is a contradiction, and hence we conclude that h2x is indeed collision resistant. Proceeding to the next problem. Let f with key space n size binary vector and input space n size binary vector. So and also output space is again n size binary. So f is a keyed function, okay, and let h which maps m to n size binary vector be a function where m is binary vector with a binary string with length at most l. L is some polynomial function of security parameter. You can just think of H to be a compression function, okay, which or maybe kind of hash function. We don't know about its security, but any arbitrary length is upper bounded by L. So any arbitrary length string is getting mapped to n bit length string by the function H. Then consider the keyed function f dash, where again the key space remains same, message space is same as the message space of H, and output also remains same. And we are defining f dash as f dash k m equal to fk of h of m. So we take the message m, which has arbitrary length upper bounded by L, and we first apply the function h on it to get a fixed length output of length n, and then we apply the keyed function fk on it to get a n-bit output. Now, which of the following is or are true? If f is a secure PRF, then f dash is a secure PRF. If h is collision resistant, then f dash is a secure PRF. If f is a secure PRF and h is collision resistant, then f dash is a secure PRF. And the last option is, even if f is secure PRF and h is collision resistant, f dash need not be secure PRF. So which one among them are true? Okay. So if we analyze the first option, if F is secure PRF, if dash is a secure PRF, they have not commented anything on the collision resistance property of H. So let's say if H is not collision resistant and F is a secure PRF, what happens then? If F is secure, okay, if H is not collision resistant, then it is easy to find M and M dash such that H of M is equal to H of M dash, right? Now let's say the adversary already knows by querying the PRF F. So it by querying the function F dash, that what is the value of F dash K on input M, that is already known. Now, because the adversary is able to come up with M dash such that H of M is equal to H of M dash, then it can, of course, answer that what is the functional value of F dash K on input M dash by seeing the value of F dash K on M, because F dash K of M is equal to F dash K of M dash. Okay. So F dash is not a secure PRF clearly. Even if F is secure, it basically turns out that M and M dash getting hashed to same value. The security of PRF no more, PRF F no more guarantees that the F dash is also secure. So the first option is not correct. If H is collision resistant, then F dash is secure PRF. This is like very trivially false statement, because as long as F is not secure, then by no means F dash can be secure, right? Even if H is collision resistant, that would at max ensure that there will be no collision pair, but the outer function Fk has to be anyway secure. Otherwise, there is no meaning to F dash being secure. Okay? So this is quite clear now that the third option is the only valid option, that if F is a secure PRF and H is collision resistant, then F dash is a secure PRF. So this is the correct option. Proceeding to the next problem. Let Gen1 H1 and Gen2 H2 be two hash functions. Define Gen H so that Gen runs Gen1 and Gen2 to obtain keys S1 and S2. Then define H of S1 S2 of X equal to H1 S1 X concatenated with H2 S2 X. Prove that if at least one of Gen H1 and Gen H2 is collision resistant, then Gen H is also collision resistant. I think this is also, if you think about it just little bit, you should get the answer yourself. So you need to prove just this one side, that if at least one of Gen H1 and Gen H2 is collision resistant, you have to hash function H1, H2. If at least one of them is collision resistant, then let's say then Gen H is not collision resistant. Let's just assume first. So we assume that H is not collision resistant even when one of H1 or H2 is collision resistant. What happens is that if we say that H is not collision resistant, that means you can come up with such pair of input, let's say X and X dash, X and X dash, such that H S1 S2 of X is equal to H S1 S2 of X dash. Okay, like this. And this will in turn imply that H1 S1 of X concatenated with H2 S2 of X is equal to H1 S1 of X dash concatenated with H2 S2 of X dash. And as you see, as both these strings are equal, this immediately shows that H1 S1 of X is equal to H1 S1 of X dash, which implies that under key S1, we are able to return collision pair X and X dash corresponding to H1. Also, we can output collision pair with respect to key S2 and for the function H2. But then at least any one of them is secure. So this cannot be true that we can so easily return collision pair for both of these functions, as at least one of the hash function is secure. So this will imply by contradiction that the construction of H is collision resistant. Otherwise, if it is not, then it is easy to return collision pair for both of the cases H1 and H2. But at least one of them is secured, so we conclude that chain H is collision resistant. Okay. Now, proceeding to the next problem. Chain H is a collision resistant hash function, and H hat is defined as H hat S of X equal to H of S of H of S of X. So we apply H with the same key S twice, and you get a new modified hash function. Whether this is collision resistant or not, that is the question. So we claim that H hat is actually collision resistant. How? So let's assume it is not again. If it is not collision resistant, then what happens that there are two cases. Basically, we output collision pair x dash in polynomial time, so that h of s of hs of hs x equal to hs of hs x dash, and this can lead to two conclusions. The first one is that h of x, hs of x and hs of x dash are equal. Because the internal values are equal, that's why applying hs again on the same input gives same output. That can be one scenario. Okay. If this is the scenario, then these two outputs are same. But then hs of x and hs of x dash are same implies x dash are collision pair with respect to hash function h as well. But this is not true because h is already given to be collision resistant. So this is a contradiction. So this option does not work. Another option when this left hand and right hand side could be same is that hs of x and hs of x dash are different. Let's say this is y and this is y dash. But applying hs on input y and on input y dash outputs same value. And what is implies? Again, it boils down to the collision resistance of H, because this is not possible for any pair of input y and y dash H of S. Like you cannot find y dash in polynomial time in like so easily. So like that, for this contradiction, we can say that H hat is collision resistant. Okay. Okay. Now, here is another problem, that for each of the following modifications to the Merkel-Target transform, determine whether the result is collision resistant. So there are two given modified construction to Merkel-Target transform. First one is written as modify the construction so that instead of outputting z equal to hs of zb concatenated with L, the algorithm outputs zb concatenated with L. If you are confused what is zb, L and z here, so let me just clarify this thing. So if you remember Merkel-Darmstadt paradigm, there are message blocks which are divided into equal length, say L length blocks, and the last blocks is corresponding to the length of the message. Let's say the last block denoted as MB plus 1 is equal to the length L, and each of the block length are of small l, and there is initialization vector IV that we denote as Z0, and it has bit length n. Now this compression function, which we later initialize with Davis-Weyr compression function, but for now let's assume there is this fixed length collision resistant compression function, which takes as input of size n plus L and outputs of size n. We apply this transformation in multiple stages, and the last stage, which includes the length of the number of message blocks. So this information is fed into the last block, is the last stage of compression function, and this output we denote as ZB plus 1. So this is what we mean by ZBL and ZB plus 1. And the question is that in this standard construction, what happens if we, instead of outputting ZB plus 1, we just output ZB concatenated with L. So we omit this part. So we don't apply the function H one more time. Rather, we take this ZB and we concatenate it with the value L with it. And whether this still remains collision resistant or not, that is the question. So just to analyze, let's say that, so this is the construction they are talking about. We don't apply H anymore. So now to find a collision in this construction, first notice that if message block numbers are not same, so you have two messages M and M dash, and length of them, say L and L dash, are not same. If that is the case, so even if ZB somehow becomes same, ZB concatenated with L and ZB concatenated with L dash will never be same, because the length L and L dash are different. So for this scenario, the collision will not happen for sure for different length messages. Now coming to same length messages, when L is same, then can there be two different such messages with same length who turns out to give same ZB value back. If that is the case, so if we analyze the scenario here, we will see that this actually boils down to the collision resistance property of the function H. Because if we need to get a collision in the value of ZB, so let's say that for some other M dash, this block M, the value of MB and ZB minus 1 here are exact equal to M dash B and Z dash B minus 1. If that is the case, then of course with the same input, it is bound to give the same output. Okay, then we look back to the previous stage. If that is not the case, then what happens is that it implies that although MB and ZB minus 1 are not exactly equal to M dash B and Z dash B minus 1, still they are giving the value ZB as output, then collision resistant property of H is failed. So H is not collision resistant. In other words, if H is collision resistant, then this we cannot easily find such two different input for which ZB are same. So because H is collision resistant, we say that this modified construction also continues to remain collision resistant based on the collision resistant property of the underlying compression function H. And in the second part, the question is, instead of using an IV, just start the computation from X1. Define Z1 equal to X1 and Zi equal to Hs Zi minus 1 concatenated with Xi for I equal to 2 to B plus 1 and output ZB plus 1 as before. So pictorially representing the scenario is like that. So in the last block, you actually no, in the first block, instead of IV, where we were saying that Z0 is IV, we are omitting that first block, and rather we start the computation from here, where M2 and M1 initialized as Z1 are fed into the H block. Notice that because instead of IV, M1 is getting fed into the first H block, there must be, so this must be the case that both these input are of same length. Let's say all the message blocks are having size n, and the function H basically takes input of size 2n and output of size n. Okay. That is okay. That is a specific case of n plus L bit mapped to n bit. that case is specified as 2n input is mapped to n bit output by the compression function. That is okay. Now, whether this changes the scenario of collision resistance. So finding collision in this function also boils down to finding collision in compression function H using the same logic as the previous problem. So without going into further details, we conclude that this construction is indeed collision resistant. Okay. Proceeding to the next problem. For each of the following constructions of a compression function H from block cipher F, either show an attack or prove collision resistance in the ideal cipher model. So let's say compression function design is given as H of kx equal to fkx, where F is the block cipher. Whether this is collision resistance or not. Let's take them one after another. So for the first one, remember in the ideal cipher model, the adversary may do standard query to the oracle or forward query with x and k and get y equal to fkx back, or it can do inverse query to the oracle with some yk and get x equal to fk inverse of y back. Now a colliding input set of the form xk and x dash k dash for the function h can be found by the following steps. So we are suggesting an attack to the system, and by this counter example, we will conclude that this particular construction of HKX is not collision resistant. So how we find the colliding input set? So let's choose X, K and K dash uniformly randomly. And we first query the oracle with forward query X and K, and we get Y back. Now we query the oracle with inverse query with y and k dash, and we get back x dash such that x dash is fk inverse of y. In other words, f of k dash on input x dash returns y. So we now have two colliding pair xk and x dash k dash such that both of them are evaluated by the block cipher f to output y. So these two are colliding pair. So thus we conclude that this is not collision resistant, the given construction. The second one, h of kx is equal to fkx XORed with k XORed with x. So if you just think of this a bit, we can readily come up with some colliding key message pair like xk, x dash k dash in this scenario. So we try to prove that this is actually indeed collision resistant, and to prove that we again see that standard oracle query with k and x returns y that is equal to fkx, and function output is computed as z equal to y XORed with k XORed with x. Inverse oracle query with k and y returns x equal to fk inverse y, and function output is computed as say z dash that is equal to y XORed with k XORed with x. Now, as we can't find any direct approach of finding such colliding pair, so let's say that let us compute probability that h of xi ki is equal to h of xj kj for some distinct value of xi xj ki kj for I less than j. So ith query, the adversary is allowed to query the block cipher used as a black box polynomial number of times. So let's say in the ith query, it queried the oracle and got to know that f of xi with respect to key ki returns some value yi, and then in some later query, say jth query, if it gets to know that f of xj with respect to key kj is returning yj, what is the probability that yj is actually equal to xj? Okay, so we write it as that h of what is the probability that yj, the output of the jth query, is equal to h of xi ki XORed with kj XORed with xj. So this is the actually the value of the hash function is yj zord with kj zord with xj, if that has to be equal to the hash value in the I query, that is h of xi comma ki, we zord both sides with this kj's or x and we get back this. So we conclude that this has a negligible probability, because you can use the same analysis when we had seen that the Davis-Meyer construction, where the standard is to use the compression function fkx zord with x. So h of x is computed at f of kx zord with x. So that Davis-Meyer construction is collision resistant. That proof included the analysis that how the previous I minus 1 number of queries to the oracle just reduces the size of possible output space by a very constant number of times in the worst case. So the basically the possibility of guessing the hash value on some new input value is still almost same as guessing the value, guessing one value uniformly randomly distributed in the output space. So using that similar kind of analysis, we can conclude that this given construction is also collision resistant. Proceeding to the third option, which is I believe very interesting. So h of kx is provided of f of kx zord with k, whether this is collision resistant or not. If you see here, so basically it is not collision resistant. The adversary can output two colliding pair xk and x dash k dash in the following step. How? So you the adversary chooses k dash y dash in such a way that y zord k is equal to y dash zord k dash. This is very easy to come up with, right? Now you query, or the adversary queries the inverse oracle with yk to get x equal to fk inverse of y back, and then it computes the function value z equal to y zord with k. And then it query the inverse oracle again with y dash k dash to get x dash equal to fk inverse y dash back, and then it compute functional value z dash equal to y dash zord k dash. And because y zord k is equal to y dash zord k dash as chosen previously, so z and z dash are same. So heads values are same, and the input pair xk and x dash k dash are distinct to each other. So like that, the adversary is able to come up with two collision input set such that the output z and z dash are equal. Thus we conclude that h is not collision resistant. So that's all for today, and thank you for attending today's session. And as I said, that 10th March will be the previous week 4 session that we missed last week. And the time will be same 6 p.m. to 8 p.m. Friday 10th March using the same Zoom link. Okay, thank you. Yes, I think you have already got access to the Excel sheet where all the live session TAs are putting their YouTube video link or the PPT Google Drive link for the PPTs. So I will upload this today or by tomorrow as YouTube link. Okay. I hope this answers your question. Yeah. Okay. Thank you. I am ending the session. Okay.